Good day. In today's lecture, we're going to be covering system calls and specifically how we can make system calls from assembly. Obviously, there is a distinction between 64-bit and 32-bit system calls, which we'll make clear during the course of this lecture. Now, a system call in many ways is requesting a specific operation to be performed by the operating system's kernel. A user process by itself cannot perform any kind of privileged instruction. For example, a user process cannot change the CPU memory mapping registers. It cannot have direct access to a hard drive, things of that extreme kind of nature. In the same kind of manner that one program should not generally be able to terminate the execution of another program, assuming, of course, it is not a child program. If a user wishes to make some kind of privileged instruction call, they are forced to utilize a system call. Now, in many ways, you can see the system call set that you have available to you as the interface to the underlying machine via the kernel. Now, the kernel itself will generally verify whether a user or process has sufficient privileges in order to actually execute the privilege instruction that they have requested. Now that we have a general idea of what a system call is, it will become informative to figure out how we can actually make calls to them via assembly. Now, for each system call, there is actually an associated integer for each of those calls. For example, the write system call in a 32-bit situation will require an integer value of 4. Now, the immediate question one has to ask is, how do I know what the corresponding integers to the system calls are? In a 32-bit context, the list of all of these functions will be found in the following H file. The location or the directory itself varies slightly, however, they are not too varied across distributions. The same can be said in a 64-bit context. There is also an interesting case of a 32-bit X system call set, which we'll not discuss in this lecture itself and will not form part of this course. Now, just to illustrate what this looks like, we can see over here that this is the list of available system calls to us in a 32-bit context. As you can see, the list is relatively extensive. Of course, I don't expect anyone to memorize this. It's something you generally look up. But you can see that there is a fairly substantial number of available system calls to you. The actual operations of each of these calls can be looked up separately. The same thing can be found for the 64-bit mode in this list here. Now, the important thing to note, and it's a common place where people make errors when they're transferring between 32-bit mode and 64-bit mode assembler programming, is that the actual integers that one uses to refer to a system call vary. For example, in a 64-bit context, the write system call has the integer value 1 corresponding to it, and in a 32-bit mode, the write system call is associated with the integer 4. So it's very careful to be sure of which mode you are currently working in and to make sure you're using the right system call. In my opinion, for the sake of this course, it is best to simply stick to the 64-bit version wherever possible. Okay, now that we know where we can find this list of available integers, the next thing that we have to do is try and figure out how we can call them via assembler. Now, for the most part, it is very similar to calling a normal function. Okay, and we discussed previously that there are certain registers which we should load in order to pass parameters to a function. Now, there is one thing that varies slightly in the context of making a system call, and that is that it uses a register that we don't normally use to pass parameters with. Specifically, we need to place the integer value that corresponds to the system call we wish to make in the EAX register, in the 32-bit context that is. Then we can utilize the normal subsequent registers to load the rest of the parameters. So in the example below, the way in which we make the system call is a little bit interesting. What we have to do is we have to actually execute an interrupt, specifically an interrupt with the value of 80 in hexadecimal. This corresponds to making a system call. In a 64-bit context, this becomes a lot simpler in that we don't make an interrupt explicitly like this, but we make use of the syscall op. Okay, but in the 32-bit mode, it's very simple. Say we want to output hello world to the terminal. All we have to do is simply load 4 into EAX, this is the system call we wish to execute, and load 1 into EBX. Now you'll immediately ask, why 1? Well, the integer value 1 corresponds to the file descriptor of the terminal. It is also possible in any Linux distribution to find the full list of file descriptors, but for the moment it is sufficient to just know that 1 is utilized for the terminal. The next thing we want to do is we want to load the address of our hello string. You'll note in this context here that we have hello world followed by a new line character. Then we also wish to load the length of this string. We do this by loading this into EDX, and then we execute the operation int 80. So the interrupt, specifically the 80th interrupt in hexadecimal. Now, for our purposes, we will generally be using 64-bit system calls, which in my opinion is a somewhat clearer way of doing things. You don't have this confusion as to know which specific interrupt is associated with making a system call. Now, in order to make the system call, we still have to load EAX with the integer that corresponds to that system call. Now, once again, as I mentioned earlier, we want to write out to the screen. However, in a 64-bit context, the integer associated with write is no longer 4, but rather 1. And again, you'll find this by looking in the corresponding H file. So we want to again output hello world to the screen. We load 1 into EAX. This is obviously the system call we wish to execute. We load 1 into EDI. Now, you could technically call both of those operations on 64-bit registers without any issue. Then we wish to load the address of hello world by simply loading that into RSI. Again, I'm using LEA for load effective address. I could have also used move and not had these square parentheses around hello. Then I want to load the length of the string into EDX, and then I call system call. Now you'll note, as with the system ABI, which we have discussed before, that the first parameter goes in EDI, second parameter goes in RSI, and third parameter goes in EDX. Again, the system calls has this extra exception case in some sense where we pass through another parameter in RAX or EAX. We then execute our system call and hello world will be output to the screen. The secondary thing we do in this little snippet is we want to terminate the program. You've seen this code before. We load 60 into EAX. This 60 corresponds to the integer for exit, which you'll find if you look in that list we discussed before. I'm going to XOR EDI. This is to indicate that I'm exiting with the code as 0. 0 is generally used to indicate that everything ended correctly. Then when I call system call, the program itself will terminate. Something I should perhaps mention to avoid a little bit of confusion is that you'll note that the parameters to which I pass the other variables here, for example, the file descriptor, the address of the hello string, and so forth, go to different registers than they did in the 32-bit case. This is a result of, in a 32-bit system, us having a different system ABI. As mentioned previously in the course, for our purposes, you need to know the 64-bit ABI, just to avoid any confusion in that context. Now, moving on, in many situations in a higher level language like C, one often doesn't actually explicitly make a system call. Instead, you work through a wrapper function. Now, every system call is actually available through a C wrapper function. Now, the wrapper function might do very little other than simply shuffle some registers about. It also sometimes helps the mapping between 64-bit and 32-bit and things like that, in the sense that you don't need to know exactly which way in which you're calling the underlying system call. And the wrapper might provide some extra convenience, might do a little bit of processing that you might automatically need to do in order to make the system call itself, but generally speaking, you can think of the C version of these system calls as simply a wrapper. You call the wrapper function executes the system call and returns back to you the result, or whatever part of that result you would need. Now, in order to understand how all the wrapper functions work, there's a very simple way to gain access to this via the actual Linux terminal. All you need to do is look at the section 2 of the online manual that corresponds to each of these C wrapper functions. For example, I can use the command man to write, which will show me section 2 of the write function, and it will explain in great detail how I can call the function, what the corresponding effects of calling the function are, and so forth. Now, in order to make a call like this, it is substantially simpler in some sense than making a direct system call. Now, if we look at the code segment below, you'll see that obviously this one is intended to be linked with GCC as opposed to LD in the previous case, and you can tell that again by the fact that we have a main function as opposed to the start function. So you first see we have defined two things here. We have a message, pretty much in line with how we had our hello before, and we have a len. Inside len, you'll see something a little interesting that we have not directly encountered before. I'll get to that shortly, but for the moment just assume that it contains the length of the hello world string, in addition to the new line character. Now, in order to make a call to the C function, write, it is very simple. All we have to do is simply use extern, and in our extern command we have to both gain access to write and exit. Now, if we want to call the write function, we simply have to load the corresponding functions for the system ABI. Specifically, we have to load RDI with the first parameter. In this case, it's 1. Again, we could have used RDI. It makes no difference. The moving to EDI is simply a smaller instruction. We then load the address of the message, and then we're going to move the length of the corresponding string into EDX. So far, this is very similar to our system call. Then we execute the operation call on the function write. This will now execute the write function for us. Now, the most noticeable difference here is that, one, I don't need to know what the corresponding integer value is for the system call write. That provides a substantial mental freedom in a sense that you're not burdened to remember all these numbers or have to look them up all the time. At the same time, you'll note that in this case, we're not loading the RAX register with anything. That is because the call of write is implicitly doing that for us. Now, if we want to exit our program, we can follow the same procedure as we did in the previous case, in that we're going to load RDI or EDI with the value 0, and then call the exit system call. Now again, we're calling it via the C wrapper, but you can visualize it as performing the system call just via the C interface. In some situations, you could argue that it is quicker to make the system call yourself directly, in that you don't have one indirection as you make the function call. However, for most practical purposes, that is not really a sufficient performance concern. Now, back to that interesting little bit of notation that we saw previously when I defined the len EQU, and that is where I have this dollar symbol. Now, we haven't encountered the dollar symbol explicitly so far in the course, but what this dollar symbol is in many sense, or in the sense is that it is the current assembly address in a byte addressable context. Now, the way in which we can exploit this little symbol to our advantage is if I write something like dollar minus the address of message, what will be loaded into len is in fact the difference between the address that len is currently lying on and that of MSG, or the message. Now, in this context, that difference inherently is the length of the message itself. This doesn't cost any computation time as it is done at the assembler phase, but it also makes it nice for us as a program in that I don't have to manually type out the number of this message. So if I added an extra character to Hello World, I don't have to now change what len actually is. Of course, it's not something you have to do, but it's a nice utility we have available to us. Now that we've gone through how to make system calls via the C wrapper interfaces, it would be informative to go through a few examples that will become useful for you in your practicals. Now, the first one we are going to discuss is the open function, and we will be using this to open files on the computer. Now, the open function takes 3 parameters, 2 of which are mandatory, the third of which is optional. The first is the path name, which is simply a null terminated string. The second is the flags. Now, you may have not directly encountered flags or had to use them, so I will expand on what the flags are for. Now, there are obviously numerous flags available to us, but some of the very commonly used ones are in the little table you see over there. The first is the flag value of 0. This means that the file you wish to open, you only want to have a read-only permission on that file while you have it open. If you have the flag value of 1, you only want to write to the file, which means you will not potentially see sensitive information in that file. The other most commonly used flag that I've seen at least is the read and write flag. This simply implies that you want to both be able to read and write from the file. You'll find a lot of people where they actually just want to read from a file will simply use this flag mode as well. That can get you into trouble if the file actually itself has a permission set such that it should not be written to. But obviously this comes down to your practical application at hand. Another commonly used flag is the 40 value, or 40 in hexadecimal. Now, this flag is to indicate that if the file you are trying to open does not in fact exist, you should create it, or the operating system should create it for you. Another flag which has, in my opinion, a slightly misleading name is the truncate flag, which corresponds to the value of 200 in hexadecimal. Now, the reason I say it's a little bit misleading is that it truncates the file to size 0. So it doesn't just chop off a little bit, as one would think when you truncate, it simply means you truncate everything and it becomes an empty file. The last flag, which is relatively commonly used, is the append flag, and that corresponds to the value of 400 in hexadecimal. Specifically, if I want to append, I mean I'm going to be adding to the information that is already present in the flag. Now, the last optional parameter is the mode. Now, the mode is used to specify the permissions you grant to the file if it is going to in fact be created. So generally speaking, you will utilize mode if you're utilizing the 40 flag from this table. Now, if you have been using Linux for any amount of time, you have probably already encountered these type of file permissions, but again, for completeness sake, I will explain them briefly. Now, there are three basic permissions that a file can have. Specifically, a file can have read permission, write permission, and execute permission. But now the immediate thing that one has to reconcile is who are these permissions necessarily being granted to. Now, Linux has a very nice classification system of three types of users. The one is the owner, or the current user that is on the system. The other is a group, where you could potentially have multiple users inside a group, and the other is deemed as other. So other simply means everything that is not in the group. Now, each of these categories will get a 0 or 1 for each basic permission. That implies that, for example, the group category will have 3 bits associated to them. Each bit will represent whether that person or that category has either read or write or execute permission. Now, since each category has 3 binary bits associated to them, octal becomes a very convenient way of representing this permission, and that is why you will generally see the permissions set using an octal value. So say, for example, I want to set the mode of a newly created file to 640. In octal this is. Now, the first digit corresponds to the binary values 110. Now, the first bit is indicative of whether or not read permission is available to the owner of the file, or the current user. So in this case, we have read permission. We also have write permission, however, we do not have execute permission. Whereas the group category, you can see, only has read permission, no write permission. This could be the same situation as if you have a few friends that you want to have access to the same file. Everyone can read it, but you don't want something to change or work. In the current situation, everyone that is not in the group or in the other category has no permissions at all. They cannot read the file, they cannot write the file, and they cannot execute the file. Moving on, it would become useful, obviously, to try and open a file. Now, the first thing we need to note is what the open function returns. Now, as you saw in the prototype in the previous slide, that the open function returns an integer. Specifically, it will return a non-negative integer that will identify the open file. More specifically, it will be the integer corresponding to the file descriptor of that file. If it returns -1, the only time that it returns a negative value is when it returns -1. This indicates that some kind of error has occurred. This could vary from the fact that the file maybe doesn't exist, you don't have sufficient privileges for the privileges you were trying to access the file with, or so on. Now, once an error does in fact occur, it will actually set a system variable called errno, which I'll discuss a little bit shortly, but for the moment you can simply rely on the fact that if you get a -1, something went wrong. Now, in the example snippet below, you'll see that we have 2 variables defined in our data section, specifically fd and name. fd is where I'll be storing the file descriptor that I retrieve after making the open system call. You'll note that it is of type dd. Specifically, it means it's a double data word, i.e. it's going to be 32 bits, and this is in line with the file or the function prototype we had in the previous slide. As you can see there, it returns an integer. Now, name here will simply be the name of the file I wish to open. Now, in this context, the file I'm opening happens to be in the local directory that I'm in, and it has no extension. And it is going to be a null terminated string, hence the 0 after the actual file name. Now, in order to call open again, we have to have the extern keyword present to make sure that we're able to successfully link. Now, we have to load our corresponding functions in line with the order in which they appear in the function prototype. Specifically, the first parameter is the path name, and that required a pointer to the path name. In our case, that simply implies we can pass the address of name into the RDI register. The second value in which I'm going to load is the flags. I'm going to load the flag of 42 in hexadecimal. Now, you'll note that that flag that you saw there is not a flag that we saw previously, but it is rather two flags, in fact, OR together. And in general, you can OR as many flags together as you want. In the extreme case, it might not be very useful, however, it is possible. Now, in this specific example, you'll see we've ORed together the 40 example or the 40 flag and the 2 flag, which means I both want to have read and write access to the file, and I want to create the file if it does not in fact exist. So hence I'm loading the value of 42 into ESI. Now, you'll note that I'm loading 42 into a 32-bit register. In some sense, it is not explicitly required that I load it into a 32-bit register, but you'll note that in the file prototype, flags is in fact an int, so it makes the most sense to load it into a 32-bit register. However, one could make the argument that because 42 is clearly not going to be larger than 32 bits, the two operations would be the same. However, I think in this case, rather make your code as concise and in line with what your own thought process is as possible, and that is why I'm loading it into a 32-bit register. Then we're going to load the mode that, or in our sense, the privileges in which that file should have once it's been created, and in this case, we are simply giving read-write permissions to the actual user or owner of the file. And for this, we load into EDX, which is the corresponding third parameter to any function call in 64-bit mode. Then to call the open function, I simply go call open, and then I have attempted to open my file. Now, once we have made the call to open, we would expect to find the file descriptor of the file we have just opened in the EAX register. Now again, it will be in the EAX register because the function open returns the file descriptor as an integer. Now, what we will do now is we compare the file descriptor to the value of 0. Now, the reason we do this is because if the value of the file descriptor happens to be less than 0, we know something went wrong. If the value we get back happens to be 0 or greater, it means we were allocated an actual file descriptor and everything can proceed as normal. So you'll see in the code there that we will jump if the comparison yielded a negative value to the error address. If that is not the case, however, I'm going to simply move my file descriptor out of my EAX register and into FD. Now, obviously, once we've opened a file, there are a couple of extra things we will want to do with the file. Specifically, we might want to read information from the file or write new information to the file. The prototypes for the two functions are nearly identical. In the first case, we pass through first the file descriptor that we retrieved from making our open function call, and then we will pass to it the address from which it should pull data from and write to the file. The last parameter is the count, and this is a long, and this is indicative of the notion that it's going to be a very big number in many situations. And this count will represent the number of bytes we wish to write or write into memory from the file. Write in many ways is the opposite of read, in that we will pass through the address of data that we currently have in the system that we wish to write to the file. We will also pass through the parameter of count, which is a number of bytes we wish to write to the file. Now, if read manages to reach the end of the file, it will return a 0 once it has reached the end of file. And both of these two functions will return a -1 on any type of error. And again, this will set the error no system flag. In order to actually get a detailed description of what went wrong, you can make use of the p-error c wrapper function to the system call. However, in most situations, you will not have to go to that extent to figure out what is wrong. Now, the second last function rather that is very useful when working with files is the lseek function. Now, this is a function that you are likely to not have had to use when you've been working in languages like C++ and Java and so forth. But what lseek does is it provides a very nice way for us to move in the file itself. You can think of us having a pointer to some location in the file, and we can use lseek to move that pointer in the file to different locations in it. Now, by default, when you open a file, that pointer will always point to the start of the file. However, lseek allows us to move that pointer around. Now, lseek takes three parameters. It takes, again, an integer which represents the file descriptor. Then it takes two more parameters. The first is the offset, and the last is the whence variable. Now, the whence variable is what gives lseek its power in many situations. Now, if whence is 0, it simply means that the location I want to seek to, or that pointer to move to, is from the start of the file plus the offset. So say, for example, my offset is 10, it will move me 10 bytes from the start of the file inside the file. If whence, however, is 1, it will produce an offset that is relative to the current position in the file. Now, obviously, the current position in the file could change if I previously made an lseek operation or certain other operations in the file. If the whence value is 2, the offset is actually relative to the end of the file. Now, that might seem a little bit counterintuitive, but it is actually a very useful option to use. Specifically, if I have the whence variable set to 2 and the offset set to 1, lseek will move all the way to the end of the file and it will return the last address in the file. Specifically, what this will mean is the value I get back is in fact the file size. So this is a very quick way of determining how big a file is. Oftentimes, if I need to dynamically allocate some amount of memory from the file in which I wish to process, it is informative to know how big the file is. So you can quickly perform an lseek operation to move to the end of the file, see how big it is, and then reset the pointer inside the file to the start again. Now, as with any type of file operations, it is always important to close your connection to the file, or in essence give it back to the operating system. Now, technically, if your process closes, the file descriptor that is associated to your processor will actually be removed. However, this puts extra burden on the kernel to do some cleanup for you. But the bigger reason, generally speaking, is that there is actually a predefined limit to how many files you can have open per process in Linux. And you can check this by using the very simple terminal command ulimit-a. Now, the reason that per process limit on a file is a meaningful limit is, say I have a program that will run for a long period of time. Somebody may open a file, save it, open a file, save it, and so on many times. And at some point, they will do it sufficiently many times for them to breach the limit, at which point the program will simply terminate, or it will fail to actually open a file, and then it will crash depending on how you have coded your program, either gracefully or potentially tragically. So it is very important to make or get yourself into the habit of actually closing the files. Now that we've gotten familiar with some of these basic operations, let us work through a nice simple example. Now, the intention of the following program is to read a file entirely into memory, then take each byte of that file and perform some kind of trivial encryption on that byte. Once this has been completed, we want to write all of that data back to the original file. So that's the general premise of this program we wish to write. Now, in order to do this, we will utilize two helper functions. The first is file size, and this we will mostly rely on our lseek knowledge that we've just gained, and then we're going to write our little encrypt function. I may be being a little liberal with the word encrypt when you see how simple the encryption is. However, in some sense, it is still encrypting the byte. Now, the file size function is now present. Now, the first thing to note as a recap, if it's been a while since you guys have worked with the assembler, is that I'm both setting up and destroying a stack frame here. The first two lines is my stack frame setup, and my last command there, this leave, is my stack frame destruction. And then finally, I return back to the program. Now, the reason I'm setting up and destroying the stack frame is because I know in this function I'm going to make use of a function. Specifically, I know I'm going to be calling lseek on a function. Now, my function for file size takes one parameter. Specifically, it will take the integer which corresponds to the file descriptor of the file I wish to get the size of. Now, once I've set up my stack frame, you will see that I subtract 16 from the stack pointer. This is because I wish to reserve space for two specific pieces of information. I want to store the file descriptor itself and then the size of the file onto the stack. Now, the reason I know I need to store these, specifically the file descriptor, is that when I make a call to lseek, I have no guarantee that what was passed through in EDI, specifically the original file descriptor, will remain, as I cannot make any guarantees that that register information will be safe across function calls. That's why I need this space. So in this case, I will reserve enough space for 2 data quads. Now, in our situation, that works out nicely in that that is exactly a multiple of 16, so we don't have to worry about additional alignment concerns. So the first thing I'm going to do is I'm going to load what is currently in EDI, which corresponds to the first parameter, into my stack memory. Specifically, it's going to be rsp plus .fd. Now, obviously, you don't need the plus fd in this context if you want to remember that it is 0. However, this is a little bit clearer as to what's going on. Then I'm going to load the 2 parameters, or the 2 additional parameters I need to make use of the lseek call. I'm going to load the first parameter, which is the offset, to be 0, and the second parameter, which is the whence parameter, to be 2. Now, if you recall from when I discussed lseek, we know that I can make a call to lseek like this to determine the file size, and that is exactly what I'm going to do now. So I call lseek, and what is returned to me in the RAX register is in fact the file size. Now I'm going to take the file size I've received and store it in my stack-based memory, specifically at the variable size on the stack. Now, you'll be wondering now, why am I bothering to save this on the stack? And the reason for that is I actually need to make another call to the lseek function. And the reason I have to make another call to the lseek function is I need to reset where the pointer was. Now, there are 2 ways in which one can choose to do this. The first is that I can perhaps reset it to its original position when I was inside this function, and that would probably be the more general approach. But for this example, we're simply going to reset the current location in the file back to the start of the file. This is done, again, by setting the offset to 0 and the whence variable to 0. I will then call lseek, and it will set the internal pointer in the file back to the start of the file. Then I can retrieve my size variable from the stack and move it onto rex, because that's what I want to return, destroy my stack frame, and then simply return. So now our function is able to retrieve the file size itself. As an interesting example, just to test that you understand what's happening, I advise that you try and recode this such that it is able to reset the original current position in the file. That would require you to potentially make an lseek before you try and make an lseek to the end of the file to save its original current position. However, for this example as it stands, that is obviously not what is happening. Now, moving on, the next helper function is our encrypt function. Now, the way in which we've decided to do this encrypt function is very straightforward, is that I have a pointer to my data of void type. Now, obviously in assembler things don't specifically have a type, so that's not really too much of a concern because we're going to be performing this encryption on a byte level. And then the second parameter is going to be the number of bytes present in this array of data. Now, the function itself is not going to return anything explicitly because we're going to change the data itself that this data variable points to. So the first thing I'm going to do is I'm going to set my count variable or my count register. Specifically, I'm going to set RCX to be 0. And then I'm going to start my looping process to loop through all of the bytes in data. So I'm going to compare RCX with RSI. Remember, RSI contains the size parameter that we pass through. So I'll check is RCX is in fact less than RCI. If it is in fact less, I will execute this loop body. If it is not, I will jump to the end while. Say, for example, RCX is in fact less than RSI. I will then extract the first byte from my data array, utilizing RCX as my index, and move this into a single byte-sized register. Specifically, I'm using AL. I will then rotate right AL by 1. The reason I decided to use something like rotate as opposed to shift is I want to be able to undo this process. Now, if I rotate every byte by 1, I can simply rotate every byte left by 1 to decrypt the file afterwards. So that's the reason we're using this approach. Once I've done this rotation, I simply return that byte I was working with back to the array from where it came. Then I'm going to increment my counter variable and then jump back to the start of my loop. And then we'll repeat this process until eventually we've exhausted the entire array. Once we have done so, we'll simply return from the function. Now note in this example, I didn't have to set up and destroy a stack frame because I didn't actually make any call to any other function. So this is in fact a leaf function. Now moving on to our actual larger program, we have the following data items that I've, for simplicity, specified in the data segment. We have a file name. This is the file we wish to actually perform the encryption on. Again, we're going to assume that it is in the local directory. I'm going to have a variable for the file descriptor of the file which I wish to open. I also will be storing the file size, and I'm also going to have an extra variable here which is data p, which I will be using to indicate that this is the pointer to my data. The reason I will have this is obviously, as I mentioned earlier, our intention is to load the entire file into memory. Now obviously if the file was a couple of terabytes, we couldn't use this exact approach, and you would have to have some more intelligent manner of taking parts of the file in at a time. But for the moment, we're working with small files. We can assume we can load the entire file into memory. Now, our program will be using a couple of functions. The first, obviously, is the lseek, which we already saw us using in my file size function. But we'll also need to use the open function in order to actually open the file. malloc, because we are not sure how big the file is, so we're going to need to dynamically allocate the appropriate amount of memory. We also need to be able to read from the file and then write back the encrypted information to the file. So in our main function, the first thing we're going to do is we're going to set up and destroy the stack frame. And again, we need to do this because we know we're going to be calling other functions. Then I'm going to move the file name into RDI and the corresponding access permission into RSI. Now, this is because I know I'm going to just wanting to be either reading or writing from the file, so I simply need to load 2 into RSI. In this case, I don't need to worry about anything like creating the file or anything of that kind. Obviously, if I didn't know the file existed, I could, for example, use 42 in hex, and then I would get that kind of functionality. However, it doesn't make too much sense to want to encrypt a file that has no content then. So in this situation, I will now have opened my file, and I will have the file descriptor returned to me in the EAX register. I'm now going to save this into my data segment because I need to make sure it is safe. You could alternatively also save this on your stack. The choice in this situation is up to you. However, I've decided to leave it in the data segment for simplicity. Then I'm going to load EDI with the file descriptor. Now, this is obviously because EDI is the first parameter to the function that we implemented earlier, specifically file size. So now I'm going to call file size. File size will return the size of the file we wish to encrypt, and then I'm going to save that value into my fsize variable. Once I've done that, I need to allocate the sufficient amount of space to store the entire file in memory. To do that, I need to call malloc, and then I'll load the file size into RDI. I then call malloc, and malloc will return to me the pointer to my newly allocated memory. That is obviously assuming that there is enough space in the system to accommodate the file in its totality. So now RAX will contain the pointer to that newly allocated memory, and we will store that pointer in my data p variable. Now that we've managed to create sufficient memory, we want to extract all the information from the file. Now, since we're loading everything into memory, this becomes very trivial in that I simply read the entire file into the memory. So I specify the file descriptor, the data pointer, and how many bytes I want to load. And I know exactly how big the file is due to my previous call to my file size function. I then call read, and it will extract all the information in that file, and it will load it into the array that data pointer points to. Now, something that I haven't explicitly mentioned before is that when I make a read call, it actually also changes the internal pointer within the file. So it changes the current position in the file. So after I performed a read like this, it makes sense for me to actually move back to the starter file if I wish to write new information to the file. Specifically, in this case, I intend to replace the entire content of the file, so I'm going to now move the current position back to the start of the file. That's what this little code segment here is doing. Once we've lseeked back to the start of the file, I now want to try and encrypt all of the information that I have currently stored in memory. So I'm going to want to call my encrypt function. I'm going to load the RDI and RSI registers with the data point and the file size, and then I'm going to call encrypt. Now encrypt will change all the information according to my rotate write encryption, And once that's completed, I can now take my entire file data that is in memory and try and write it back to the file. Now, because we've reset the current position over here to be at the start of the file, in order to write everything to the file, it's very straightforward. All I have to do is load the file descriptor into EDI, the data point into RSI, and the file size into RDX. Again, this corresponds to the parameter order, and then I call write. This will load everything back into the file. Then once this is completed, I can simply call leave to destroy my stack frame and then return. Now, one should immediately look at this and think that I'm missing something. And I'm not missing just one thing, I'm actually missing two things. The first thing that I'm missing is that I never closed the file. Now, that is obviously something that I discussed before, and that's something you should do. So if you are to work at home on this specific example, I encourage you to try and add that little bit of functionality to actually close the file descriptor or your link to the file descriptor. The second thing which I haven't done is I haven't deallocated the memory that I've allocated with malloc. So that is the second thing I would like you to try and add to this example when you actually go home. So now that brings us to the end of this lecture on system calls via C interfaces.